Imagine you have this like massive multi-gigabyte data file that you need your computer to read.
Oh, total nightmare for RAM.
Right. So you test two different algorithms to do the job. One is this lightweight, streamlined reader that just sips memory.
Okay.
And the other is, well, it's a brute force memory hog that tries to swallow the entire file all at once. Now, the streamlined one should obviously win the race, right?
I mean, yeah, that is just basic software logic right there.
Exactly.
Yeah.
But today, we are looking at a real-world scenario where that memory hog absolutely demolished the lightweight reader. And the reason why exposes a massive blind spot in how almost all of us think about writing code.
It totally does. It completely upends the way we're taught to evaluate software. Because, we are conditioned to think of code in terms of absolute mathematical certainty. Like a faster algorithm equals faster execution.
Right. It's supposed to be that simple.
Yeah, but when you step into the real world of hardware level execution, that neat little equation just shatters.
And that reality check is our mission for you today. We are doing a deep dive into a highly technical but incredibly fascinating presentation from 2026 by an engineer going by the handle Luck03A6.
Yeah, the presentation is titled Streaming JSON SAX Parsing for Yosys Netlists.
Which sounds intense, I know. But we have their slide deck in front of us, and it details how to efficiently translate massive hardware blueprints into usable digital formats. And the coolest part, they wrote the exact same tool using two different languages.
Python and C++C, which is such a rare treat. Seeing the same logic implemented across different environments is what actually reveals these hidden performance traps.
Oh, for sure.
And while the topic sounds intensely specific to hardware engineering, the core lessons buried in these slides, they really apply to anyone who writes code or optimizes systems or just cares about why technology sometimes behaves so unpredictably.
Yeah, so if you are someone who lives for those aha moments, and you love understanding how things actually work under the hood without drowning in unnecessary jargon, this deep dive is tailor-made for you. Because we are going to uncover that counterintuitive truth about software performance. Okay, let's unpack this, starting with the arena we are operating in. What exactly is a Yosys netlist, and why are we trying to parse it?
Right, so Yosys is essentially the industry standard open source synthesis tool for hardware description languages, things like Verilog and VHDL.
Got it. And for those of you who might not be familiar, those are essentially the programming languages used to design physical computer chips, right?
Exactly. You don't build a microchip by drawing wires by hand anymore. You write code that describes how the chip should behave. And Yosys is the engine that takes that high-level, human-readable description and synthesizes it down into something physically real.
So if I'm understanding this, I can think of Yosys as an incredibly literal city planner.
Oh, I like that. How so?
Well, I give it a vague request. Say, I want a residential neighborhood that connects to a commercial district. Yosys takes that request and synthesizes the actual blueprint. It calculates exactly where every single pipe, electrical wire, and intersection needs to go so the city actually functions.
That analogy works perfectly for the synthesis process. And once Yosys does all that complex calculation, it spits out a few different files.
Okay, what kind of files?
Well, it generates a netlist, which is a structural graph of all the logical cells and the wires connecting them. Then it generates Liberty files.
Liberty files?
Yeah, those hold the complex timing and power models so the chip doesn't, overheat or misfire.
Ah, important.
Very. And third, and this is the entire focus of our deep dive today, it generates a JSON output. This is a machine-readable, plain text blueprint of that exact circuit description.
And just to give you a sense of scale as you're listening, these are not your typical little web configuration files. We are talking about massive, sprawling documents, millions of lines of text representing the entire architecture of a computer chip.
Right, it's huge.
And keeping with that city planner idea, the cells it maps out are the microscopic buildings, things like logic gates and flip-flops, which are tiny hardware memory storage units. And the ports are like the highways leading out of town, handling the input and output of data.
Yeah, and like any complex city blueprint, this JSON file has a very specific, rigid structure. It's defined by a master document called yosysschema.json.
Right, the schema.
Exactly. When you look at the structure in the slides, you see those key entities organized hierarchically. You have the ports, the cells, the net names for named wires, and the connections, which represent the actual physical wiring between everything.
Now, I'm looking at the slide showing the JSON structure for these connections, and I'm noticing something that seems like a trap.
Oh, what are you saying?
Most of these wiring connections are mapped with integer numbers. like wire ID 5 connects to wire ID 10.
Yeah.
But scattered in here, there are string values. I'm seeing a literal 0 and a 1 wrapped in quotation marks.
Good catch.
If I'm writing a parser and I just blindly read this JSON, mapping every single thing I find as a wire, aren't those strings going to break my whole graph?
They absolutely will. Those strings are not wire IDs. They are hard-coded electrical constants representing a wire tied directly to ground or directly to power.
Oh, wow. Okay.
Yeah, so if your software tries to map an electrical constant as a physical, routable wire between two logic gates, your structural graph gets totally corrupted. You'd be telling the chip manufacturer to build a physical bridge to a concept rather than a location.
Which means whoever is reading this massive blueprint needs to be smart enough to filter the data on the fly. Like, we need to ignore the decorative trees and only map the actual roads.
Precisely.
But because these JSON blueprints are millions of lines long, we run into a physical limitation. I mean, if a file is larger than the available RAM on your computer, how do you even open it to read it?
And that right there is the crux of the problem. It brings us to the two distinct parsing strategies that the author, Luck036, evaluates. Because when you're dealing with data this massive, the mechanics of how you read it dictates whether your program succeeds or just flat out crashes.
Okay, so what are the two contenders?
The two contenders are DOM parsing and SAX parsing. DOM stands for Document Object Model.
Right, DOM.
This is the simple, familiar way almost every programmer first learns to interact with JSON. You write a command like json.load, and the computer attempts to read the entire file, build a massive interconnected tree structure of all that data in its active memory, and then hands it to you to query.
So DOM is essentially like trying to memorize an entire encyclopedia before you are allowed to answer a single question about a topic inside it.
That's a great way to put it. The benefit is that once that encyclopedia is fully memorized in your RAM, you can jump around instantly. You can check a wire on page 500, then instantly check a port on page 2.
Super fast once it's loaded.
Exactly. But the fatal flaw is memory capacity. If the encyclopedia is too big, your computer simply runs out of space, starts thrashing its hard drive to compensate, and eventually the whole system crashes.
He just gives up.
Yeah. And that is why the alternative is SSX, which stands for Streaming API for XML, though it applies perfectly to JSON here as well.
So if DOM is memorizing the whole encyclopedia, SX must be a totally different mechanical approach.
It is. SAX doesn't load the file into memory at all. It reads the data sequentially, byte by byte, as an event stream.
An event stream, like it triggers things.
Exactly. It sees an open bracket, and it fires an event to your code saying, hey, an object just started. It sees a string, it fires an event saying, hey, I found a word.
So it's like reading that massive encyclopedia page by page and just writing down the exact notes you need on a small notepad. And once you turn the page, the parser completely forgets what it just read. You only keep your little notepad.
Yes, it is incredibly memory efficient. What's fascinating here is the trade-off. Because SAX has absolutely no memory of the whole document, the burden of context shifts entirely onto you, the programmer.
Oh, because the parser doesn't know where it is anymore.
Right, you have to build a custom state machine.
A state machine?
Yeah.
That sounds intense. What does that actually mean in this context?
It means you have to write code that constantly tracks its own location based on those tiny events. You have to write logic that says, okay, I just saw an open curly bracket, and before that I saw the word cells, which means I am currently inside a cell definition, which means the next number I see is a cell ID, not a port ID.
Wow, okay. That introduces a massive cognitive load for the developer.
It really does. You aren't just querying data anymore. You are building an architectural engine just to safely traverse the data stream.
So you're trading heavy memory overhead for heavy architectural complexity.
Exactly.
And to see how this complex SAX state machine is actually built in practice, the presentation walks us through implementing it in one of the most popular programming languages on Earth, Python.
Yes. Python is universally loved because it is readable, expressive, and highly accessible. But as we know, it is not a compiled language, it's interpreted.
Right, which means it isn't exactly known for blazing fast execution speeds.
True. But for this streaming task, the author utilized a specialized Python library called ISON. The way ISON works is by feeding the programmer triples of data as it streams through the file. It hands you a prefix, an event, and a value.
Okay, breaking that down mechanically, the event might be something like start map when it sees a curly brace or end array for a closing square bracket.
Yep.
And the value is the actual data, like the name of a wire or a numeric ID. But the real heavy lifting seems to be that prefix.
Oh, the prefix is where iShine shines. It actively tracks the hierarchy for you and hands you a string showing exactly where you are in the document tree.
So it does some of the state tracking for you.
Exactly. It gives you a string like modules.mychip.cells.gate1. So as your Python code receives this relentless stream of events, you just use those prefixes to filter and catch the specific pieces of data you care about.
Okay, so we've successfully streamed the file and grabbed our data without overloading our RAM. But simply reading the data isn't the final goal. We have to take that small notepad of data and functionally rebuild that city map, the netlist graph.
Right, you still need the final product.
And in the slides, this is called Phase 2 graph assembly. Looking at the methodology here, it's not just randomly throwing data together. There's a very specific sequence.
There has to be, because the relationships in hardware are incredibly complex. After streaming, the Python script executes 5 distinct assembly steps to rebuild the map.
Okay, what's step 1?
First, it takes all the collected net IDs, the wires, and sorts them, assigning them internal graph node indices.
Wait, I've got to ask, why sort them first? Why not just start plugging them in as you read them?
Because hardware is basically a massive spider web of logic. If you just throw data in as it arrives, your memory allocation becomes scattered and traversal gets incredibly slow.
See.
Sorting them first ensures you create predictable, ordered nodes in memory before you start drawing the complex web between them.
That makes perfect sense. You're setting a solid foundation.
Exactly. Step 2 is spinning up a NetworkX graph. NetworkX is a standard Python library used for studying complex networks.
Right.
A computer chip's wiring is highly nonlinear, so a graph structure is mathematically perfect for analyzing how a signal traverses from point A to point B.
And step 3?
Step 3, it iterates through its nodes and adds mathematical edges between the cells and the nets. Step 4, it adds edges between the fixed I/O ports and the nets. And finally, step 5, it wraps all of this mapped logic into a tidy netlist Python object.
So the end result is a highly usable, structurally sound graph of the microchip, perfectly identical to what the memory hawking DOM approach would have produced. But we achieved it through a lean sequential methodology.
That's the goal.
But wait, I'm looking at this Python logic and I have a serious question about how it actually stops.
Okay, what's the issue?
If Python is reading this massive stream sequentially, piece by piece, doesn't it just keep reading until the literal end of the file? Like if a Yosys file contains multiple microchip modules, multiple cities, to use our analogy, what if we only want to analyze the very first one?
That is a critical piece of the puzzle. Hardware designs almost always contain submodules, tiny cities within the larger city. But for many top-level analysis tasks, you only need the main blueprint.
Right.
So, the state machine in this script is designed with a strict first module only rule. It is actively looking for the boundaries of that first module. Once it hits the closing bracket of that first module, it deliberately resets its states and essentially ignores the rest of the file to save processing time.
But because it's Python, it's still technically reading the rest of the file, right?
Yes.
It's just choosing to ignore the events. Like it's walking through the rest of the city with its eyes closed, but it still has to physically walk the whole way.
Precisely. It avoids processing the data into the graph, but the disk I/O and the event generation are still happening under the hood.
Which brings up a fascinating comparison. Python is managing this with the JSON library, those handy prefix strings. But what happens if we strip away all those conveniences?
It gets a lot more raw.
Yeah. What happens when a lower level, fundamentally faster language handles the exact same state machine logic? This is where the presentation shifts gears to C++ key, and we get to see how close to the metal coding changes the mechanics of parsing.
Right, so the C++ implementation relies on a highly regarded library called nloman.json. And unlike Python's iJSON, this C++ library has a native built-in SAX handler.
Meaning what, exactly?
Meaning you don't just get a stream of data strings, you write highly specific callback functions. You tell the compiler exactly what function to execute when an object starts, when a key is read, or when a number is found.
But without that handy prefix string that Python gave us, how does C++ track context? If I'm millions of lines deep into a file full of curly brackets, how does the C++ parser know if it's looking at a cell ID or a port ID?
That is where the author had to implement something brilliant mechanically, a path stack. Since C++ isn't formatting a neat prefix string for you, the code has to dynamically build its own context map on the fly.
How does a stack actually accomplish that?
Well, a stack is a last in, first out data structure. Every time the SX parser fires a start object callback, the C++ code pushes the current key name onto the top of the stack.
Okay,
So it pushes modules, then it pushes my chip, then it pushes cells. When it finally hits an end object callback, it simply pops the top name off the stack.
I see.
By looking at whatever is currently resting on the stack, the program dynamically pieces together a dot-separated path that is functionally identical to what Python provided natively.
So what does this all mean? The C++ path stack is basically a trail of breadcrumbs.
That's exactly what it is.
Every time you walk deeper into the forest and open a bracket, you drop a crumb with a name on it. When you turn around and close the bracket, you pick that specific crumb back up. That way, no matter how deep into the file you go, you can always look at your hand and know exactly where you are without ever memorizing the whole map.
It's an incredibly elegant and efficient way to manage state. And because we are operating in C++ EAT, we gain access to a fantastic low-level optimization for that first module only rule we just talked about.
Oh, right. Remember how Python just closed its eyes but kept walking?
Right. Python kept reading the file but just ignored the events. In the C++1 Loman library, you have much more control over the hardware.
How so?
When you are collecting net IDs and you realize you have finished the first module, returning a simple Boolean false from any of your SAX callback functions acts as a hard abort.
Wait, really?
Yes, it instantly signals the parser to stop reading bytes from the file entirely. It literally stops the disk I/O dead in its tracks.
Wow. That is the true power of being close to the metal. You aren't just ignoring the data. You pull the literal plug on the file reader the second you have what you need.
Exactly.
Okay, so the stage is set. We have the exact same logic, the exact same state machine, written in two very different languages. The native C++ approach and the interpreted Python approach.
And then they tested them.
Right, the author ran both of these alongside the brute force DOM parsing method through rigorous benchmarks, 50 iterations each to ensure mathematical accuracy. Let's look at the results.
This is where our assumptions get severely tested. They ran 3 different Yosys JSON files of increasing size. Let's start with the smallest file, called yosysan2.json. It's tiny.
And the result.
A virtual tie across the board, about 0.38 milliseconds for both DOM and SAX in both languages.
Which makes mechanical sense. The file is so small that the overhead of setting up the SAX engine takes roughly the same amount of time as just cramming the whole file into memory. It's like renting a massive industrial crane to pick up a single pebble, you know?
Right.
The time it takes to turn the crane's engine on is longer than just bending down to pick it up yourself.
Exactly. The methodology doesn't matter when the data is trivial, but then they move to a medium-sized file, sphere.netlist.json. Here, the theoretical advantage of SAX becomes incredibly obvious.
Let me guess. SS1.
Big time. In Python, the streamlined SAX approach was 1.6 times faster than the Python DOM 19.3 milliseconds versus 31.5 milliseconds. And in C++ SAC, the victory was an absolute blowout. C++ SAX was a whopping 5 times faster than C++ DOM 4.8 milliseconds compared to 24.1.
Okay, so the lean mean SAX algorithm is the clear winner for larger files. The math checks out. We have our neat binary software truth.
Not quite.
Well,
They ran a third file, a massive complex blueprint called Sphere3hoff. In C++, the SAX approach won again, about 1.6 times faster than C++ DOM. But in Python, the memory-hogging brute force DOM approach actually beat the streamlined Python SAX.
wait.
DOM finished the massive file in 59.2 milliseconds. The lightweight SAX algorithm dragged behind at 88.3 milliseconds.
Okay, wait. Here's where it gets really interesting. How is that mechanically possible? We just established that DOM has to load the entire massive file into RAM. How could that brute force memory hogging approach possibly beat the highly optimized SAX machine in Python on the biggest file they tested?
This is the grand takeaway of the whole presentation, and it all comes down to understanding how a programming language physically interacts with your computer CPU.
Okay, lay it on me.
Python is an interpreted language. That means it doesn't compile down to machine code beforehand. It translates your code into instructions on the fly, line by line, while the program is running.
Okay, I follow that. It's translating in real time.
Now, think about what SX is doing. Every single time the parser finds a bracket or a word or a number in this multi-gigabyte file, it fires an event. That event has to be caught and processed by a pure Python event loop.
Oh boy.
Yeah. On a massive file, SAX generates an astronomical number of these tiny microevents. Because Python is translating on the fly, every single tiny bracket triggers a whole sequence of translation work.
So it's just overwhelmed.
Exactly. The overhead of the Python interpreter simply trying to manage millions of context switches eventually bogs down the entire CPU. Python spends more time translating, hey, I found a bracket, than it does actually reading the data.
So the Python translation engine itself becomes the bottleneck, not the algorithm.
Precisely. Meanwhile, how does the DOM approach work in Python? It uses the standard JSON.load library. But under the hood, that standard library isn't actually running pure Python. It is written in highly optimized, pre-compiled C code.
Oh, that's a massive detail.
Right, so when you call DOM in Python, it hands the heavy lifting off to a lightning-fast C backend. That C code brute forces the massive tree into memory, allocates a huge block of RAM all at once, and then hands the finished object back to Python.
Wow.
On the medium file, the overhead of Python creating all those memory objects made DOM slower. But on the huge file, the sheer volume of Python-level SAX events was so overwhelming to the interpreter that the brute force memory allocation of the C backend actually became the faster path.
That is mind-blowing. The slower algorithm won because the runtime environment punished the faster algorithm's mechanics.
Okay.
I mean, SAX only fulfills its theoretical promise when the execution environment is native and close to the metal, like C++ pay.
It perfectly illustrates why benchmarking in your actual production environment is mandatory. You cannot just pick an algorithm from a textbook, assume it will be faster because the math says so, and call it a day.
Absolutely. We've definitively proven that the environment matters more than the theoretical algorithm. But, that assumes the parser was built perfectly to begin with.
Right.
The author didn't just guess how to build this state machine. They used that master document we mentioned earlier, the schema. But looking at the final slides of the presentation, relying on a schema actually reveals another massive trap for developers.
Yeah, the author spent time analyzing Yosys schema.json to see what it actually helped with during development and what it completely failed to provide. And this is a really vital lesson in software architecture.
Okay, so what did it help with?
Well, a schema is incredibly useful for making high-level implementation decisions. Because Lux036 read the schema, they knew they had to filter out those string constants using a function like isNumberInteger when looking at the wire connections.
Oh, they knew about the trap we spotted earlier.
Yes. They also knew that the ports and cell sections were strictly required for the file to be valid, so they knew exactly which subtrees their state machine needed to watch. They also learned they could completely ignore optional metadata, like the creator key, saving processing time.
So the schema is fantastic for reconnaissance.
Yeah.
It tells you exactly what the terrain looks like before you land.
Exactly.
But what did it fail to do?
If we connect this to the bigger picture, the schema did absolutely zero to help design the mechanics of the actual SAX state machine. It didn't help with the callback sequencing, it didn't provide any logic for isolating the first module, and it certainly didn't help write the complex mathematical graph assembly algorithm in phase 2.
Because a schema is just a specification. It's a design document. It tells you what you are aiming at and what the final product should theoretically look like, but it doesn't tell you how to build the engine to get there. It's like having a picture of a completed car. That doesn't mean you know how to build a transmission. Intimately understanding the mechanics of the data format is what leads to a correct parser, not just blindly importing a schema file and expecting it to write the runtime logic for you.
That's a vital distinction. The schema is the map. The state machine is the vehicle you have to build yourself to traverse it.
And what a deeply complex vehicle it turned out to be.
So, to bring this all together for you listening, the real beauty of this deep dive isn't just learning about Yosys blueprints or the nuances of SX parsing. It is the power of the dual language pattern.
Without a doubt.
By taking the exact same algorithmic logic and writing it in two completely different languages, the author exposed entirely hidden trade-offs that most developers never see.
It forces us to question our deepest assumptions. A methodology that is universally praised in computer science textbooks as efficient, like SAX, can actually degrade your system's performance if the underlying interpreter isn't built to handle that specific type of load. The algorithm doesn't exist in a vacuum. Context is everything. Context is everything. Which leads me to a final thought for you to mull over. Today, we saw that a complex, highly optimized SAX state machine only really shines when it's running close to the metal in C++ day, while an interpreted language like Python might actually favor the simpler brute force DOM approach for massive files.
Yeah.
We are moving rapidly into an era where AI is writing more and more of our parsing code for us. When you ask a chatbot to optimize your file reader, will that AI be smart enough to understand these deeply hardware-level execution trade-offs? Or will it just blindly recommend the theoretically faster algorithm, completely ignoring the reality of the interpreter it's running on? Will it build you a sports car without realizing you were driving on a dirt road, something to chew on the next time you blindly accept an AI's code optimization?